In our study of calculus so far, we've looked at basic differentiation and integration. We viewed integration as simply a mechanical process to reverse differentiation or to find the area trapped under a curve. We're now going to move our knowledge and understanding on and look at some of the more advanced applications of integration. Before we do that though, we need to build up a new skill set. We need the tools to allow us to integrate expressions and equations that we've not met before. Over the next set of videos, we're going to look at some of these new expressions and find different ways to integrate them. The idea of the set of videos is to allow you to spot which particular expression or equation you have and then which technique you need to use. So let's do a bit of recapping. Say we had a polynomial f of x. If we wanted to integrate that now, all we would do is raise by a power and divide by a new power. In general, we could say that the integral of x to the power of n with respect to x was given now as x to the power of n plus 1 divided by n plus 1 plus a constant of integration. We said that n could not be equal to minus 1 as we couldn't divide by 0. So all we did was raise by a power and divided by the new power. That allowed us to integrate polynomials term by term and simply work through basic examples. So for example now, if we were asked to integrate x cubed plus 2x squared plus 3x plus 1, and we were asked to integrate this now with respect to x, we would go along and we'd raise by a power and divide by the new power. So 1 over 4x to the 4th plus 2 over 3 x to the 3rd plus 3 over 2 x to the power of 2 plus x plus a constant of integration. And there are a whole host of different problems that we were given like this. We're now going to move things on, and the first part that we're going to look at is what we call integration by recognition. So let's go ahead and look now at an example of how we can use integration by recognition. Say I had now the integral of, let's just say I had the integral of x plus 2 all squared. So we wanted to integrate that. Now before you would have expanded this out and that would have been nice and straightforward. This would have given you now the integral of x squared plus now 4x plus 4, and we would integrate that term by term and it would be nice and straightforward. Now let's say I change that over and let's say I did something along the lines of, let's say I had 2 lots now, and I'll just make these up as I go so we can just work through some basic examples. Say we had this. Now I don't want to use a binomial expansion on this to go ahead and do this term by term. I don't want to say that it's going to be x to the 5th and then 4 to the 0 plus 5 x to the 4th, 4 to the 1st and so on. We need a new technique. Now in our work before we've met what we call the chain rule. The chain rule allows us to differentiate functions of a function. This is a function of a function and we can use integration by recognition to undo this. So if we have now the derivative with respect to x of g of now f of x. So this is a function of a function. So in our case, we've got 2 functions here. We've got x to the 5th and x plus 4. So if you like, g of x would be x to the 5th and the f of x would be x plus 4. We saw that the derivative of this now was g dashed, and then we had the f of x, and then we had now multiplied through by f dashed of x. So let's put this in layman's terms. Or layman's terms, I should say. We differentiated the outside function, we rewrote the inside function and multiply through by the derivative of the inside function. So let's take something along this line. So let's say we had now 3 and then we had x plus 2 to the power of 4. So what we did, we multiplied down by the power. So we had 4 lots of 3 lots of x plus 2. We dropped the power by 1 and multiplied through by the derivative of the inside function. So we could now say informally this was going to be 12 the quantity x plus 2 to the power of 3. Now we can use integration by recognition to actually reverse this process. So let's go ahead and look at doing that with this particular case. Now you're probably thinking to yourself, well, where is the derivative of the inside function? Just consider that the derivative of x plus 4 with respect to x is 1. So what I'm going to do is rewrite this, and often I bring the constant to the left. So 2 is a constant. We're going to look now at x plus 4 to the power of 5, and we're integrating that with respect to x. So before I saw now but I differentiated the outside function, I rewrote the inside function, I multiplied through by the derivative of the inside function. Therefore, what I'm going to get when I do this, if we consider now, I'm going to get two lots. This time, I'm going to integrate the outside function. So I get x plus 4, I raise by a power, and I divide by the new power, and I'm going to write this now as 1 over 6. And then I divide through by the derivative of the inside function. The derivative of x plus 4 is 1. And that's what we end up with. We need, of course, to add a constant of integration. So when I've differentiated the outside function, rewritten the inside function, multiplied through by the derivative of the inside function. This time I've integrated the outside function. I've divided through now by the derivative of the inside function. So what I end up with then is the following. What we've got here, now if we look at this, we're going to have 2 over 6, which is going to be now 1/3 the quantity x plus 4 to the power of 6 plus our constant of integration. And of course, if we wanted to go ahead and find the derivative of this, we'd multiply down by the power, so we'd have 6 lots of 1/3. We'd rewrite the inside function, drop the power by 1, and then multiply through by the derivative. So you can see we're going to get now 2 the quantity x plus 4 to the power of 5 as we had before. So that's simply now reversing the chain rule. And we can apply this to far more complicated problems. So if you want now a formal definition, and I don't really like this, what we can say is the integral of g dashed of f, and we'll write this in, let's write this in, f of x multiplied now by f dashed of x, or anything along these lines. We might have something that looks like that. What we can say, if we're integrating that with respect to x, we're going to end up now with the g of f of x plus a constant. I find that slightly too informal, but I've done it for completeness. All we're doing now is simply saying, if we are integrating a function of a function, given its derivative, then this is what we're going to get. So let's look at that in action, okay? So it does look quite daunting, but as you'll see, we'll start spotting things as we go. So let's look at an example now. Now let's do one here. I'm going to say that I've got 3x, and then I'm going to have, let's go for x squared plus now, let's go for plus 3, and we'll raise this to the power 4, and we'll integrate that with respect to x. So I want the integral of that. Now, integration by recognition is often a case of saying to yourself, can I spot that this outside here is some form? It doesn't have to be the exact derivative, as we'll see later, but some form of the derivative of the inside function. If it is, I'm going to now try and use integration by recognition. Sometimes you'll use integration by substitution, but for now it looks like I can integrate this by recognition. So what I'm going to do is write this out. I'm going to write 3x. I'm going to write now x squared plus 3. I'm now going to raise this by a power. That will give me now to the 5th power. I'm going to divide by the new power. Then I'm going to divide through by the derivative of the inside function. So what I'm doing is reversing the process. So I'm going to end up now with 2x. As we can see, these x's are going to cancel. So the x's are going to cancel, and I'm going to be left now with 3 over 10. So 3 over 10, the quantity x squared plus 3 to the power of 5 plus a constant of integration. So you can see that I've reversed that process. What I've done is integrated now. I've integrated, I've raised by a power, divided by the new power, and divided by through by the derivative of the inside function. With the chain rule, we differentiated the outside function, rewrote the inside function, and then multiplied through. This time we're just simply reversing that process. So we could have done that one by recognition. So if you want to go ahead and just differentiate this, we're going to get 5 lots of 3 over 10. Then we'd have now x squared plus 3, drop the power by 1, multiply through by the derivative now of the inside function, which is going to be 2x. And we can see now that that's going to leave us exactly what we started with from there. 5 times by 2 is 10. 10 over 10 is just going to give us now the 1. So we're going to end up now with 3x, and then we're going to have x squared plus now 3 to the power 4. So you can see now I am reversing the chain rule. This is just spotting now that this here is some derivative of this. Okay, let's look now, let's write a harder example. So let's try something slightly different. Let's go for the integral now, and we'll say that this is going to be the integral now of 2x plus 4 over now the quantity. Let's write this as 2x squared. Let's go for 2x squared plus 8x, and then we'll have minus 3 to the power of 2. Now we'll integrate this with respect to x. Now if this wasn't here, if this wasn't a 2 and that was just a 1, we'd look later at now a function where we integrate and we end up with an answer that involves logs. But for now, because this power is not just 1, we're going to use reverse of the chain. Now at the moment this doesn't look blindingly obvious. But if we consider what I've got here, I've got two lots of, and I'm going to write this now, and we could write this as 2x plus 4. I'm going to write this now. In fact, I'll write it as it is. Let's just write 2x plus 4. Now, what I've got here is 2x squared plus 8x minus 3 to the power of minus 2. That is what I'm looking for. So, this is actually the integral that I'm after, okay? So what I'm going to do is just simply write 2x plus 4. Then, what I'm going to do is write the inside function again. So I'm going to integrate the outside function, which is going to give me now minus 1. So I'm raising by a power, I'm dividing by the new power, and then I'm going to divide through by the derivative of the inside function. Now the derivative of this is going to be 4x plus 8. So we're going to get now 4x plus 8. So all I'm doing is reversing the process. Now, let's just look at factoring this a little. Let's go ahead, and remember, I'm going to add a constant of integration. I'll do that at the end. So if we look at this now, I'm going to have minus, and I'll take the 2 out here. We're going to have x plus 2. Now, if I then bring this over, what I've got, if I take now the 4 out of this, I've got now 4x plus 2, and then I've got this now, which is going to be the 2x squared plus 8x minus 3 to the power of minus 1. Now we can see these are going to cancel, these x plus 2's. So we could actually write this now as 1/2 the quantity 2x squared plus 8x minus 3 to the power of minus 1. Or, and again, remember this has got a constant of integration, we could write this as minus 1 over 2 lots of 2x squared plus 8x minus 3. And if we were asked to find the derivative of that, then we would go ahead and just simply now apply the chain rule. So what we'd have, if we were asked to find the derivative, we'd have minus 1/2 the quantity now 2x squared plus 8x minus 3 to the power minus 1. Multiplied down by the power, that's going to give us positive 1/2. Rewrite the inside function, 2x squared plus 8x minus 3. Drop the power by 1, which is minus 2, and multiply through by the derivative of the inside function, which is going to be 4x plus now the 8. So let's go ahead and do that. What we can see, half of this is going to give me now 2x plus 4, and then what we're going to have is this right here, which we can write now as 2x squared plus 8x minus 3. So by recognition, we've reversed now the chain rule. So that is one application and slightly harder to spot, but you can see from there that it quite clearly works. Okay, let's move this on and extend it to different functions. So let's go and have a look at e to the x. Now, if we looked at e to the x, say we've got the derivative with respect to x of e to the x, we saw that this was e to the x. We've seen that in our previous modules. So what we're now going to do is look at the integral. So what we can say then is the integral of e to the x with respect to x is simply going to be e to the x plus a constant. Now we can extend this where we have a function of a function. So let's look at a function of a function. Let's say I've got now, let's say I've got e to the, let's say I've got 3x plus 1. Okay, now if I wanted to find the derivative of this, what I'm going to end up with now is the following. I'm going to end up with 3 lots of e to the 3x plus 1. So again, we've differentiated the outside function. rewritten the inside function, and then multiplied through by the derivative of the inside function. And that's something I'm kind of assuming that you'd be comfortable with certainly from previous topics. So let's look at another one. If we had the derivative with respect to x of e to the x squared plus 3x, the derivative now would be 2x plus now 3 multiplied by e to the x squared plus now 3x plus a constant. And I should, of course, have added my constant just there. So that's what we've got. That's what we're integrating. Now, in general, what we can say is the following. If we have the integral, and let's just write this out, and again, this is quite daunting. What we have now, if we have constant k, if we have the integral now of k, f dashed of x, multiplied now by e to the f of x dx, what we're going to end up with now is simply ke to the f of x plus a constant. Now that seems like a lot of hassle. That seems like a really, just simply a lot of it's a lot of hassle. But let's look at that in action. Let's look now at the integral of 2x, and then we're going to have e to the x squared plus 4. Now, if I wanted to integrate this with respect to x, automatically what I'm saying to myself is, hang on a moment, that is now the derivative or some form of the derivative of this inside function. So all I'm going to do now is the following. I'm going to write that this is going to be 2x e to the x squared plus 4 divided through by the derivative of the inside function, which is 2x. And as you can see now, that's going to give me e to the x squared plus 4 plus a constant. And again, if you were asked to find the derivative, you'd multiply through by the derivative of the inside function. So nice and straightforward. It's logical, it works, and you can see by recognition, as long as you're saying, well, that's some, for example, that is some derivative of the inside function, therefore we can reverse the chain rule and simply employ this. So as you can see, this is spotting it. So instead of using a substitution, instead of going through quite a tough set of steps, we can just simply recognise this. Now, if that had been over here, for example, 8, that wouldn't have mattered. If we had, for example, now let's say 8x e to the x squared plus 4, all we would do is just write this. So if I wanted that, now generally I'd take the constant the other side as well. What I'd say then is we'd have 8x e to the x squared plus 4 divided now by the derivative, which is 2x. So we can see that this would actually be 4e to the x squared plus 4 plus a constant. So that's what I've got. Now, if you go ahead and differentiate this, you can see what's going to happen. We're going to end up with what we started with. So that's now looking at using the chain rule in reverse for the exponential function. So let's look at something that might be even more challenging. Let's go for, and I'll write this one out, let's go for the integral of, let's go for the quantity of 3x squared plus 2x multiplied now, and let's say we've got e to the 2x cubed, and then I'm going to have plus 2x, and we'll go for 2x squared, plus now 7. Say we want now the integral of this with respect to x. Now, I'm looking at this saying 3x squared plus 2x. I'm thinking to myself, that might be some form of the derivative of this inside function. So let's go ahead and look at this. So 3x squared plus 2x multiplied now by e to the 2x cubed plus 2x squared plus 7. Now I'm going to divide through by the derivative of this inside function. Remember, the derivative or the integral of e to the x is e to the x. So if we have now e to the u, the integral will be e to the u. So now I'm going to divide through by the derivative of the inside function. So with the chain rule, I've multiplied through by the derivative. With now the integral, I'm dividing. So what we're going to have then is 6x squared plus now 4x. So let's go ahead and look at that now. Now I could actually write this as follows. I could write now 3x squared plus 2x. Now if we look at this, we can of course factor this. Taking a common factor of 2 out, that's going to give me now 3x squared plus 2x. And of course I've now got my e to the 2x cubed plus 2x squared plus 7 plus a constant. They're going to cancel. So we can see that the integral is actually 1/2 e to the 2x cubed plus 2x squared plus 7 plus a constant. And that now is spotting yet again that this is some form of the derivative of the inside function. So that's another example of that in play. So all we've done is gone ahead and used now the chain rule. So let's now move on and look at something slightly different. And later on we'll come back to doing a few more of these. What we're now going to do is extend this to some trig expressions. Now it's important not to get carried away right here. Lots of trig integration needs different techniques, but sometimes we could go ahead and use integration by recognition. So let's choose something. Let's say the derivative with respect to x of sine cubed x. Now we use the chain rule on this, and we could say that this was actually the derivative with respect to x of sine of x all cubed. So just revisit the chain rule and essentially look at what happens with this. So we multiply down by the power, we're differentiating the outside function, rewriting the inside function, and multiplying through by the derivative of the inside function. So we're going to get 3 sine x, which we drop the power by 1, and multiply through by cos x. So I've differentiated the outside function and multiplied through by the derivative of the inside function. So let's say we got the following. Let's say we had now the integral of 3 cos x, and then we had sine squared x. Now looking at this, I'm saying to myself, well, hang on a moment, this now is the integral of sine x, therefore it looks like I could reverse the chain rule on this. As stated, it's not always going to be the case, but what we would essentially do is look at this now as 3, then we'd have cos x, and we'd have now sine of x to the power of 2. So in this particular case, and it's not in general, and I'll show you an example later where it's not a general. If we get now 3 cos x, we're going to now raise by a power, divide by the new power, and divide through by the derivative of the inside function. So what we get is now raising by a power, we get to the third power, dividing through by the new power, which is 3, and then dividing through by the derivative of the inside function, which is cos x. So by recognition, we should be able to see now that the 3's are going to cancel, now the cos x's are going to cancel, and we're going to be left now with sine of x all cubed, or sine cubed x plus a constant. So that's a nice way of doing it. You can just spot that. Do be aware though, now if you had sine squared x here, and we were asked to integrate that with respect to x, then we've got no product here. We've got no product of the derivative and the original function. So we've got no f dashed of x multiplied by f of x going on here. Now, as a side note, we'll come on to this later, but one way to integrate this is to use a trig identity. Now, we know a trig identity, cos 2x will be equal to 1 minus 2 sine squared x. So we could say now that we could rewrite this as 1/2 1 minus cos 2x. So we're not able yet to integrate powers of sine in or cosine in this form. So what we do is just rearrange this and integrate that right there. And later on we will look at this. Now just out of interest, if you differentiate cos 2x, again, using the chain rule, what we end up with now is minus 2 sine 2x, as we saw in the previous unit. And we'll start looking at trig functions in another video. So that's a nice example of that one in action. Okay, let's see if we can be quite cheeky and do another example. Let's say I had now the integral. Let's go for the integral of 1/4, and then we had, let's go for sec squared x tan x. So let's integrate this with respect to x. Now that looks a complete mess, okay? Now straight off I'm thinking to myself, I might use a trig identity. We know that, for example, a trig identity is sec squared x will be equal to tan squared x plus 1. And often in later examples we will come on to use identities. Now let's consider the derivative with respect to x of sec x. The derivative with respect to x of sec x is sec x tan x. So what I've got now is sec x tan x. Now, can I manipulate this so that it looks a bit like this? Well, yeah, I kind of can. I can write that this is actually 1/4 sec x, and then we've got tan x multiplied by sec x. Now, this again gives rise to a chain rule. So what I'm going to do is reverse this. So I'm going to write this now as 1 over 4 sec x tan x, and then I'm going to raise this by a power. So I'm going to have sec x to the power of 2 divided by the new power divided through by the derivative of the inside function, which is sec x tan x. So by recognition, and this is subtle, we can see now that these are going to cancel. So what I would have here now is 1 over 8, the quantity now sec, or 1 over 8, I'm going to just write it as sec squared x plus a constant. Now if you go ahead and differentiate that, multiply it down by the power, drop the power by 1, multiply through by the derivative of the inside function, we have this. So that is very, very subtle, massively subtle, and often you'll be led into it, or you'll be given an identity. But that essentially is reversing the chain rule. Okay, so let's finish the video, and I'll just work through a few more examples. So let's go for now, and I'll just write a few more to kind of recap what we were doing. So let's go for 2x, and then we're going to have, let's go for x squared minus 5, and we'll go for the power of 3 dx. So what I'm going to end up with then is the following. Rewriting, I'm going to have 2x, I'm going to have x squared minus 5. I'm going to raise by a power, I'm going to divide by the new power, I'm going to divide by the derivative of the inside function and add a constant of integration. So from this we can see that this is going to give me now the 2x is going to cancel with the 2x, so we can have 1 over 4, the quantity now, x squared minus 5 to the power of 4 plus a constant. I've simply reversed the chain rule. Okay, if we looked at another, let's make something slightly harder. Let's go for, let's have x squared plus 2 now over, and let's take the quantity. Let's go for x cubed plus 6x. Let's see if I can get this one to work. This looks to be a bit messier. Now, what I'm going to do with this is just rewrite this. I'm going to write this as x squared plus 2 multiplied by the quantity x cubed plus 6x to the power of minus 1/2, and we're going to integrate that with respect to x. So let's go ahead and see if I can reverse now the chain rule on this and do it by inspection. So x squared plus 2, then I'm going to have now x cubed plus 6x to the power, raise it by a power, that's going to give me positive 1/2, divide by the new power. Dividing by half is multiplying by 2, and then dividing through by the derivative of the inside function, which is going to give me 3x squared plus now, what we can have, plus 6, plus a constant of integration. So if I just tidy this up, what I've got now is the following, and I'll bring the constants over here. I've got now 2 the quantity x squared plus 2, and I'm just going to factor this right here, taking the common factor now of 3 out. I'm going to have 3 lots of x squared plus 2, and then I've got this right here, which is going to be the x cubed plus 6x to the power of positive 1/2 plus a constant. So we can see now that these are going to cancel, and we could just simply write this now as 2/3 root of x cubed plus 6x plus a constant, or any equivalent. So all I've done is simply reverse the chain rule. So that's kind of quite cute and quite nice. But again, you might be given a substitution. The reason I was able to do this is that I spotted now that this was some form of derivative of now this inside function. Again, this is not the power of 1. If that is the power of 1, you're going to have to use now log integration. And that's when we have, and I'll just write this one out for future reference, if we have the derivative or some form of it in the numerator and the function in the denominator, we end up now, if we're integrating this with respect to x, we have the natural log of the modulus of the f of x plus a constant. And in a later video, we'll see that in action. Okay, let's have a look at a couple more before we go. Let's look at now the integral of 1/3, and let's go for sine x, and then we'll say now cos to the 5th x. Now, with a bit of rearranging, what we can do with this one is write 1/3. Now, we're going to have sine x, then I'm going to raise by a power, so this will be cos to the power of 6x divided by that new power, and then divided, so that should look like a 6, there we go, and divided through by the derivative of the inside function. Now remember, this was written as cos x to the power of 6. The inside function is cos x. The derivative is minus sine x. And remember, we need now to be careful with that. So what we're going to get here is minus 1 over 18. We can consider now these sine x's are going to cancel, and then cos to the power of 6x plus a constant. So that's a nice example of that one in play. Let's look at another one. I'm just kind of jotting these as I go. Let's go for the integral of 4e to the 2x minus 3. We'll integrate that now with respect to x. So all we're going to have then is the following. We're going to have 4e to the 2x minus 3 divided by the derivative of 2x minus 3, which is 2. So that's going to give us now 2e to the 2x minus 3 plus a constant. Let's go for something slightly hard. Let's make this slightly nicer. Two lots now of cos x. So we'll look at two lots of cos x, e, and then we'll go for sine x plus, now, let's say we've got 4, and let's integrate that with respect to x. Now, look at this here. We know that the derivative of sine x plus 4 is cos x. So it looks like we can use now the chain rule to reverse this. So let's go ahead and do that. So what we're going to do is write 2 cos x. We'll have e to the sine x plus 4 divided through by the derivative of sine x plus 4, which is cos x, and then we'll have our constant of integration. So we can say that this is 2e to the sine x plus 4 plus a constant. And of course, if you go ahead and differentiate that, multiply through by the derivative of the inside function, that's what we end up with. So fairly logical, fairly straightforward. Let's just do one more. Let's do now x plus 1. So the integral of x plus 1, e to the x squared. So e to the, let's go for x squared plus 2x. And then let's go for, just have that with respect to x. So I'm going to have x plus 1. Then I'm going to have e to the x squared plus 2x divided through by the derivative of the inside function, which is 2x plus 2. We can see that's going to factor, so we're going to have x plus 1 over now 2x plus 1, and then we'll have e to the x squared plus 2x plus a constant, and we can see those cancel off to give us now 1/2 e to the x squared plus 2x plus a constant. So there we go. That now is using the reversal of the chain rule, or just spotting these functions now, or expressions, just spotting them and working backwards. Integration by recognition. Often this topic will be merged with substitution, and for harder examples you will be given a substitution. So a couple of those that I've done, you might be prompted, but if you can recognise that we've got some product here now of the derivative multiplied by the original function, now then we can look at reversing the chain rule or simply doing integration by recognition.